How about a made-up physics problem? So in this problem, I am on the moon because who wouldn't want to be on the moon, right? I'm on the moon and I throw an object straight up, and I don't really know too much about this. I just made up some numbers, may not work out, but I have a 1 kilogram object and I throw it up, which is, this is the way it's up, at a speed of 100 meters per second. So the question is, how high will it go before it comes back down? Now, you may say, hey, this isn't too bad. I could calculate the force. I could say, here's my, up is to the side here, and I'm sticking with that, okay? So here's my mass. There's my gravitational force. Yes, G is smaller because it's on the Earth. I mean, the moon, not the Earth, but it's still a force, and it has some initial velocity that way, v1, and then I can just find the acceleration and use my kinematic equations. But can you really do that? No, you can't. I mean, you may be able to. I'm not really sure. It may work. And we'll check at the end. But the problem is that as this mass moves further away, the gravitational force changes, right? The real gravitational force, the magnitude, looks like this. G, m of the moon, m over r squared. So as r, the distance from the center to here, increases, the gravitational force decreases, so the acceleration changes. So you have a problem here, that this is a difficult situation because it's a non-constant force. Now, there is a way to deal with that, and I'll show you how. There's more than one way to deal with that. And I'll show you one of the ways, but I want to show you the best way to think about this problem, and that's to use work energy. So since I don't care about time, I don't care how long it takes, and since I'm dealing with two positions, position 1, and up here at the highest point, position 2, and I don't care about direction, those three things say I should use the work energy principle. This says that the work done on a system is the change in energy. That's the work. I know it looks dumb. Okay. So let's first define work. The work done by a force is the force dot the displacement, or you could write that as the magnitude of the force, the magnitude of the displacement delta r times cosine theta, where theta is the angle between the force and the displacement. So if I have some system and I push on it, then I'm going to change the energy of that system. That's what this says. Now, what about the energy? Well, the energy depends on what kind of system we have. So let's say that we have the system of the, I guess it's a ball. It's a ball plus the moon. In that case, I have no external forces on my system, right? There is a gravitational force on the ball, but there's also a gravitational force on the moon from the ball. And so as these things move apart, then that's an internal force, and it doesn't do work on the system. It doesn't change the energy of the system. So I don't have a work done on the system. That's only force. So the work is 0. What about the change in energy? Well, we have a couple types of energy here. We have the change in kinetic energy and the change in potential energy. So since I have the Earth, I mean the moon, I'm sorry, it's the moon. Look, it's got craters on it and everything. Since I have the moon and the object in my system, then I'll have a gravitational potential energy. And since the ball is moving, I'll have a change in kinetic energy. So we define kinetic energy as 1/2 mv squared. It's a scalar value. And then we define the potential energy for a system of the ball and the moon as U equals negative G m of the moon, mass of the object, over r. That's an important one right there. You know, you can say, well, why is it negative? Why isn't it r squared? It looks a lot like that. It's got the G, it's got the two masses. Well, this is actually an energy, and that's a magnitude of a force. So they're different things. Why is it negative? Well, when you calculate it, you get a negative, but also think about this. If I move towards the moon, my r value gets smaller, so potential gets to be a bigger number. But I want this to be a decreasing of potential. And so the only way, one way I can do that is to have a negative potential, right? Because if I'm moving this way, this value doesn't get larger, but it's still decreasing because it's getting more and more negative. Okay. I'll make a video deriving that without calculus. You can derive it with calculus too, and I have a video on that too if that's what you want. So I have two types of change in energy, change in kinetic, change in potential, going from here to there, and I can use that to find out how high that is. So let's just set this up. with a new piece of paper. Oh, and I have the mass, the radius of the moon, the mass of the moon, and the gravitational constant. So here's the system I have. Let's draw the picture again. Here's position 1, and it's moving with the velocity v1. I don't care about the as a vector because it's not a vector problem. And then I have position 2, and it has v2 equals 0. Right? At the highest point, it's going to be 0. And I want to find this distance h, but the equation really deals with this, r1 and r2, the distance from the center. So I have the work energy equation says 0 is the change in kinetic, k2 minus k1, that's change in kinetic, plus u2 minus u1, the change in potential. One of these terms is 0. Well, and it's the k2, right? Because up here it has 0 velocity, so that's 0. So now I get 0 equals negative k1, which is negative 1/2 m. I'm using lowercase m for the mass of the object, v1 squared. And then I have u2, which is this potential energy at that position. So it's negative, so I'm going to say negative g mass of the moon, the mass, over r2. And we'll put in r2 in a little bit. And then I have minus the potential over here, but that's also negative, so it's going to be minus a negative, so it's going to be plus g mass of the moon, mass, over r1, which is just the radius of the moon. Now I want to solve this for r2, so let's go ahead and solve this for r2. I'm going to add this term, since it's negative, to both sides of the equation. So I get g, if I add that to 0, I get g mass of the moon, mass of the object, over r2 equals, I'm going to switch the order of these because that way I have it looks nice. It just looks nice, right? G mass of the moon, mass, over r1, which is just the radius of the moon. I'm going to use rm, minus 1/2 m v1 squared. Okay, so if I divide both sides by the mass of the object, it cancels. So that's good. Okay, now I want to divide, I want to find r2, right? So I'm going to essentially cross multiply. I hate saying that, but I'm gonna multiply both sides of this equation by r2, and then I'm gonna divide both sides of the equation by that. And that looks bad, but they're just numbers, so it's not that big of a deal. So let's just do that. So I get g mass of the moon, and then I need to divide by all that, divided by g mass of the moon over rm, minus 1/2 v1 squared, and that's going to be equal to r2, right? Because there's, once I divide by all that. That looks bad. I know. That's fine. And that's equal to the radius of the moon plus h. So if I want to solve for h, I can subtract rm, and I'm done. H equals g mass of the moon over this messy stuff, g mass of the moon over the radius of the moon, minus 1/2 v1 squared, all of that minus the radius of the moon. Let's just check real quick, right? Let's check to make sure our units are working out right. So here I have g. On the top here I have g, which is Newton meter squared per kilogram squared, times the mass. So I get Newton meter squared per kilogram. Down here I have Newton meter, same thing, but divided by a meter. So I get a Newton meter per kilogram. And now Newton, 1 Newton, is equal to 1 kilogram meter per second squared. Meter squared per second squared. No, 1, that's right, meter per second squared. Okay, so this is, oh, the Newton. Oh, I'm going to, the units do work, I'm pretty sure. I don't want to get, it's messy because I have to switch over there. And I should have even gone down there and like, hey, you're just leading us down the wrong path. And I get that. Okay. So I have all my values. I'm just going to plug in my values here. Now, you could do this in a calculator, but since I'm going to use Python anyway, I'd rather switch over to Python and show you how awesome it is to use Python for a calculation like this. Okay, so here I have Python. I've already entered in some details. Ooh, that's really glary. I have g, the gravitational constant. I have the mass of the moon, the radius of the moon. I need v1. v1 equals 100. Now what I can do is just type in that equation that I just saw. I'm going to say H equals, I'm going to just type it like I see it. G times mm divided by G times mm divided by Rm minus 0.5 times V1 squared. You see how that looks nice? And then minus Rm. Now I can print that. Print H equals H meters. And let's run this and see what happens. Okay, so I get 3,000 meters, 3,083 meters. Now, what if the gravitational force was constant? So let's calculate G. Because remember, G is the gravitational force at the surface divided by the mass. So it's G, mass of the moon, over R, radius of the moon squared. This is not, I'm talking about lowercase g. So G equals G times the mass of the moon divided by the radius of the moon squared. And let's print that. G equals, it should be about 1/6 the Earth, G, in newtons per kilogram. Okay, so that looks 1/6. Yeah. Okay. So now, what if it had a constant acceleration? I'm going to do this really quickly. If it had a constant acceleration and we wanted to find out how high it went, we could find the acceleration, which would be g, negative g. I know the initial velocity, and now I can choose the kinematic equation, which says the final velocity squared is the initial velocity squared plus 2a change in y. So the change in y, I put dy, which I'm going to use something different. It's going to be equal to, okay, let's write this out. I'm going to make a mistake. So let's switch back over to the paper. Okay, so back on the paper, if it's moving with an initial velocity v1, and over here it has a final velocity of v2 equals 0, and this is delta y, then I have v1 squared equals v2 squared is v1 squared minus 2g delta y. And so in this case, that's 0. So 2g delta y is equal to v1 squared. Delta y is going to be equal to v1 squared over 2g. So now I can plug that in, and let's just see what happens. I need to switch here. Okay, so I'm going to just type in my equation, v1 squared divided by 2 times g. Print that. Print d. I'm going to call it dy. dy meters. Let's see how those two numbers compare. So you see what I get here. It actually goes higher with the real gravitational force than it did with the constant gravitational force. But the constant gravitational force is pretty realistic, pretty a good approximation. Now, but what if I increase the speed to 1,000 meters per second instead of 100? I was trying to think of something I could actually throw. I can't throw it 100 meters per second anyway. So if I change this, my calculations are still legitimate. And if I run it, now what happens? I get a difference, right? So different by 70,000 meters. So this one goes 374,000 meters high, and this only goes 307,000 meters high. So it does matter in that case. Okay, now I did tell you that I would do this another way, and I'm going to do it another way. So let me jump back over to the paper and show you how to do this the other way, because even if I have a changing gravitational force, I can still model that by breaking into small time steps. And I've done this before, so if you've never seen this before, I'll include a link to another video. But suppose I have a velocity v1 and I have a force f, and those are vectors. Then I can say this, f net, and I'm going to do this the acceleration way, even though I prefer the momentum way most of the time. F net is going to be ma, which is m delta v over delta t. If the time interval is small, then the force doesn't really change that much, and I can just say the acceleration is a change in velocity or the change in time. And this is going to be m v2 minus v1 over delta t. That's going to be my change in velocity. v2 is the velocity at the end of the time interval. v1 is the velocity at the beginning of the time interval. If I solve this for v2, I get v2 equals v1 plus, now I need to multiply both sides by delta t, divide by m, and so I get f net over m delta t. Now, if I assume the velocity is constant, I can say velocity is a change in position with respect to time. So v, this is going to be equal to r2 minus r1 over delta t. So r1 is the position at the beginning of the time interval, r2 is at the end, and if I solve this, I get r2 equals r1 plus v2 delta t. So I just calculated the velocity at the end of the time interval, so I'm going to use that as the velocity during the whole time interval. That seems dumb, I get it, but that's what I'm going to do. And then I can say t2 equals t1 plus delta t. And then if I do that for 1 second, the ball hasn't gone far enough, so I need to go up here, recalculate the gravitational force because it's got a new position, update the velocity, update the position, update time, and do this again. Okay, and we can make a model of this too. So let's jump in here and let's just do this whole thing. I'm going to do this as fast as I can, but if I'm going to give you the code. You pause this and you do it the way you like. Okay, the first thing I'm going to do is to make the moon. So let's say the moon equals sphere, position equals vector 0, 0, 0. I'll put it at the origin. I'm going to keep it there. The radius is equal to rm. And let's just run it like that and see what happens. So if I do that, there's my moon. And it's shiny and everything. It doesn't look like the moon, but that's fine. Okay, now let's make the ball. Let's make it also a sphere. Let's put it on the edge of the moon. So its position, I'm going to go in the x direction. The position is going to be vector rm 0, 0. And now I got to make it big so you can see it. So I can see the radius is equal to rm over 20, and let's make it yellow so you can see it. Color.yellow, and let's leave a trail. So say make trail equals true. I can't remember if that's capitalized or not. Okay, so there's my ball, giant ball. Now I need to give the ball a mass, which I technically already did. No, I didn't. So ball.m equals 100. As if it was 1. I need to give it an initial velocity. Ball.v equals vector. I wanted to go in the positive x direction, so it's 1,000, 0, 0. That's what I want to do. And I think I'm ready to, I need t. T equals 0. dt equals, let's say 1. Okay. Now, I don't want all that stuff, so let's leave it there. Let's do it this way. While t less than 50 seconds. I'm just picking a number. Rate 100. That will be really fast. That'll take 5 seconds. If I do, rate tells me how many loops to do every second. So if I do a time step of 1 and I'm going up to 50, so let's just do 100 and make this 500, and that'll take. Let's do this as 500. No, let's do 100. I can't decide. Okay, so the first thing I'm going to do is to calculate the gravitational force on the ball as a vector. So I'm going to say F equals G times mass of the moon times the ball's mass, times the ball's mass, ball dot m, times r hat, negative. Let's do this. R equals ball.pos minus moon.pos. So ball.pos is the vector location of the ball. Moon.pos is the vector location of the moon. Even though the moon's at the origin, this will make a vector from the center of the moon to the ball. And that way, if the moon moves, this will still work. Okay, but you don't have to do that. And then I can say norm r. So norm r returns a vector, unit vector, in the direction of r. And we need that to turn this force back into a vector. And then I need to divide by the magnitude of r squared. And that's my gravitational force. Now I'm going to use that to update the velocity. Ball.v equals ball.v plus f times dt divided by ball.m. So ball f divided by ball.m is the acceleration. This right here looks confusing because that's an update statement. It's not an equal to statement. It makes it equal to, so it updates the velocity. I don't have to keep track of all the indices. Now I need to move the position. Ball.pos equals ball.pos plus ball.v times dt. Update time, t equals t plus dt. That's it. I didn't save it. I should save it, shouldn't I? Ball toss on moon, save. And you will get the code. And yes, I've done things like this a bunch of times. Okay, so now I'm going to run it. And there you go. Okay, so let's print the final position. That didn't even take that long. So I'm going to say print ball POS equals ball.pos in meters. So it goes up and it went. Oh, that's not H. That's the position. Okay, that's the final position. Let's print H. Ball H equals. It's going to be equal to the radius of the moon minus let's put the magnitude. Okay, so did it stop? No. Why is that negative? 3. I should subtract the radius. I did it backwards. That's fine. Okay. Let's just throw it a little bit faster, because who cares? So let's change this to 3. And it's not stopped, so that's not as high as it's going to go. But that's just how far we threw it. If we want to find out how high it goes, I'm going to say while the magnitude, let's do this. While ball.v.x is greater than 0. Because once it becomes back this way, it'll stop. Oh, I went too fast. Okay, let's change that back to 1,000. And there you go. And that's it, right? That's the same value. I got the same value for height. It did work. Pretty happy. Okay. So, but the work energy way is a lot better because you don't need to do a numerical calculation. We can deal with changing forces. It's the best way to go.